A Chinese space station is currently falling towards the Earth, and no one really knows when and where it will hit. And so, since this is a somewhat current event and it will probably fall pretty soon, I decided that today, instead of talking about rocket design theory, which I might as well do later, I would talk a little bit about this, explain why exactly this is so hard to predict, clear up a few misconceptions or misunderstandings, and explain the physics behind why this is so hard to predict. Now, I'll try to make this somewhat comprehensive. There is, of course, a lot to tell about this, and there have been other videos before this, like Scott Manley has already made a video about this, so I'll be somewhat focusing on things that I think haven't been said that often yet. But while I'll focus on the physics, first of all, a very brief refresher on what is actually happening and what it actually means. Now, a few images have been thrown around about this on the internet, more or less wrong mostly. Some of them got some things right, but much of it was somewhat clickbaity, much of it was misunderstood or based on false information, and people then do their conclusions from that, so there's a lot of false ideas about this going around. So let's clear this up. First of all, obviously, this is not the International Space Station. This is a Chinese space station. Yes, there is more than one space station. In fact, there's even more than one Chinese space station, and I'll once mention its name now, but I'll probably pronounce it wrong, so I'll try to avoid it mostly. Its name is the Tiangong 1, and there is already a successor, the Tiangong 2. And first of all, while I think it's obvious to most people who have some interest in spaceflight and most people who will see this, I still think I should probably mention that there's no reason to panic. It's not an imminent threat to everyone on Earth, and just in general, keep calm. Just in case that someone might be panicking right now, I think it's helpful to just mention this information, although it might be obvious to most people. This is a relatively small space station. There probably will not be anything left after re-entry, although a few minor parts might survive, like the really big parts will mostly melt off during re-entry, but a tiny piece of these really big parts might survive re-entry, so you might have a tiny screw falling from the sky at some place, though of course no one knows exactly where yet, and probabilistically it's unlikely to land anywhere near civilization or a human. While this is not a controlled re-entry and this is bigger than many satellites, it's really closer in size to a satellite than to most other space stations that you commonly know about, like the ISS or Mir or Skylab. The second misconception is that this is some kind of major mishap, which it isn't. This space station was decommissioned, it's no longer in use. There's a successor space station in use now. Also, unlike some people think, this is not a trashy design or anything. It's a well-working space station, it's just a little bit outdated. They built a new one, and now they're getting rid of this one. And then at some point a minor mishap occurred. They no longer have contact to the space station, they no longer have direct control over the space station, but that's really a low priority. You don't really need to have control over a space station that you no longer use. Now to the orbital mechanics, how can something fall out of orbit? Now, of course, in an orbit is as such gravitationally stable. Like the gravity, the orbital mechanics keep it stable as such, so you could go around the Earth forever, but there's the problem of atmospheric drag, and that's the atmosphere doesn't suddenly cut off at some point. It gets gradually thinner and thinner and thinner as you go up, and actually low Earth orbit is still within the highest parts of the atmosphere. It's no longer officially called the atmosphere, but there are some very thin gases around that cause some very minor amount of drag that slows satellites or space stations at this low altitude down. Now, most communication satellites are in geostationary orbit, much higher up. There's no such thing as a perfect vacuum nowhere in the universe, but it's so thin that for the next few centuries you don't really have to care about the atmosphere in geostationary orbit. In low Earth orbit, however, there's enough atmosphere left to actually make an orbiting satellite or space station fall down within a matter of months. Now this is still usually referred to as a stable orbit as long as there's enough time left and as long as you have the infrastructure to reboost your satellites or space stations. The International Space Station, for example, is regularly boosted up by some spaceship docked to it. It's not a very spectacular maneuver, it happens at very low thrust, very slowly, so it doesn't disturb much. Of course, the International Space Station isn't really built for gravitational influence or to experience high acceleration, so it's a very low thrust maneuver, but it's slowly boosted up once every few months to prevent it from further drifting down into the atmosphere. Now, without this happening, a decommissioned space station will start drifting downwards. This happens also at a very low force. The aerodynamic force up there is, of course, incredibly low, so you don't get suddenly slowed down, you get slowed down over months, over several orbits, and as long as the speed difference within one orbit is relatively small, you can approximate this as a sort of constant sinking or a constant spiral. And of course, orbital mechanics, it's a bit contradictory. If you slow down, you end up speeding up because you drift downwards, and Kepler orbits, the lower you get, the faster you get. But the overall result is that your orbit just keeps sinking and slightly circularizing. Now, the orbit of the Chinese space station is still somewhat elliptical, it's not perfectly circular, but the lower it gets, the closer it gets to circular, because if you've played Kerbal Space Program before or have a basic grasp of orbital mechanics, if you slow down at some point in your orbit, that will affect the altitude of the opposite side of your orbit. If you slow down at one point, the opposite side of the orbit will be lowered, and if you speed up at some point, the opposite side of your orbit will be raised. Now, the lower you are, the denser the atmosphere you are in, so the more you slow down, and so overall that has a tendency to circularize your orbit. But it's not suddenly going to turn your orbit into a perfect circle, rather it's going to slowly reduce your eccentricity. Now this is where we come to the first issue as to why this is so hard to predict, and there are really many reasons as to why it's hard to predict, which all kind of add up to one another, which is why you might hear different explanations for it, and also why it's really so incredibly hard to predict, because yeah, there are several reasons to why it's difficult, adding up to one another, so it's like extra difficult. It's a sort of amplified double exponential, but it's hard to exactly explain in mathematical terms because this does get pretty complicated. But first thing to keep in mind, the atmosphere does gradually decline as you go up and gradually get thicker as you go down, but this doesn't happen linearly, this happens exponentially. At ground level or reasonable aviation-like altitudes, you can roughly approximate that using something like an ideal gas equation or similar approximations, or just look it up on Wikipedia, and you'll see that roughly every 20 kilometers you go up, the atmosphere will decrease in density by a factor of 10, and then another 20 kilometers up, again a factor of 10, so in 20 kilometers altitude the atmosphere is about 1/10 as dense as it is here where I sit. At 40 kilometers altitude it's about 100th as dense. At 60 kilometers altitude it's about 1,000th as dense. This turns a lot more complicated when you go to really low pressures and temperatures as you do at this high altitude, and it kind of speeds up at some point, slows down again. It's not exactly exponential anymore, there are a few other factors, but roughly speaking it's still an exponential function with a few modifiers in it. But this exponential function is again overlaid with what's basically another exponential function, because the lower the space station gets, the deeper into the atmosphere it goes and the thicker the atmosphere gets. And that means that the space station will be slowed down and lowered even faster. So the lower it gets, the faster it will fall, which is also basically an exponential equation, but it's based on another exponential equation which describes the density of the atmosphere. And that alone makes it very hard to predict, to the point where something like an over-the-head calculation is pretty much absolutely pointless. You can kind of track the curve at which it is currently declining and see when it will go further down, but without an incredibly accurate atmospheric model and an averaging and data point analysis function that requires at least a computer, over-the-head calculations are gonna give you something like anywhere between the next 10 minutes and the next 10 years. It's pretty pointless, but With some data analysis and some knowledge of the atmosphere, you can kind of tell that it's gonna be a few days, but not exactly how far. Now, many professionals have calculated this with exact models of the space station and current meteorologic data and quite a bit of computer work, and currently the prediction stands at April 1st, somewhere around early noon, which of course also leads to the common misconception that this is an April Fool's joke. It's not. But the thing is, while these predictions get more and more accurate, at the moment this is in 2 days, and the predictions are still plus minus 12 hours or something like that. Because there's a lot more factors that make this hard to predict. For once, it's very high up, so the atmospheric expansion will affect it a lot. What this basically means is, if the atmosphere is a little bit warmer, then it will basically expand as warm gases expand, which means that since this is around 200 kilometers up, and say the atmosphere gets thinner for every 20 kilometers you go up by a factor of 10, that means if the atmosphere is warmer and thus more expanded by only 10%, that is over this altitude a difference of 20 kilometers or a factor of 10. So a misestimate in one factor by 10% ends up affecting the end result by a factor of 10 instead. And then you also have to take into account things like the shape of the Earth and advanced orbital dynamics, like the orbit is still not perfectly circular. It still has a lower point and a higher point, and those are on opposite sides. The lowest point of the orbit is on the opposite side of the Earth as the highest point of the orbit, but as the orbit is changed through this aerodynamic drag, these shift around the orbit. And now it's interesting to know, is the lowest point on the night side of Earth or on the day side of Earth, because that affects the temperature and the expansion of the atmosphere. What's the current weather? What's the current weather gonna be in 2 days? That alone is pretty hard to predict. As Scott Manley had already pointed out, the Earth isn't perfectly spherical. Its diameter at the equator is about 10 kilometers more than its distance between the poles. So is the highest point and the lowest point at the equator, or are they at the more inclined points and the equator is at average altitude? Because the atmospheric density is an exponential function, that has a lot of effect. If the highest point and lowest point are on the equator, that will make the stations fall faster than if the average points are on the equator. But while you could look that up for right now on satellite trackers, this keeps changing and you'd have to keep predicting that over the entire time. Of course, I should mention that you can track the descent and the current location of the space station on sites like N2YO or SatFlare, or you can just Google Tiangong 1 and satellite tracking, or just go to any satellite tracking site and to news. They'll probably have a short text about it and a link to that object tracker. And another nice thing we have is radar images of the space station, and that brings us to the next point, the shape of the space station and its structure, and that also makes it hard to predict. The aerodynamics of incredibly thin gases at incredibly high speeds are complicated enough. We don't know exactly where the center of mass of this thing is, and as it goes deeper into the atmosphere, the aerodynamic forces will make it spin. They might stabilize it in some direction, they might keep it spinning in all directions or only in two directions, and of course it has different cross-sections along all directions. If it flies like straight forward, it essentially will have less drag than if it points its solar panels right into the wind. And at some point it will start breaking up, which will make its solar panels break loose. That will probably be the first thing to fall off, and those will then fall down a lot faster than the rest of the station, which will then start falling down slower because it has lost a lot of drag. And at the moment we really can't predict when exactly those solar panels will actually fall off the station. Then the really big issue is that we can impossibly tell where it is going to hit, because this again is an amplified version of trying to tell when it will hit. Keep in mind this thing is circling the Earth at actually a slightly higher speed than the ISS, roughly every 90 minutes. So if you make an estimation error of when it is going to hit by about 45 minutes, that means that your estimation to where it is going to hit is going to be on the opposite side of the Earth, because it just flies halfway around the Earth in 45 minutes. So not only are our predictions for when it is going to fall down relatively unprecise, but they also have an extreme impact on where it is going to fall down, because, well, it's moving fast. Now, I'll have to mention that it only moves fast in one direction. It only moves fast in a circle around the Earth, while the motion alongside that circle is the Earth spinning away under it. So we can exclude a few areas. You can see a model of the ground track right now, and if you've seen things like the ground track of the ISS or some low Earth orbit satellites before, you've seen that they kind of circle the Earth, and after one round around the Earth they get back to almost the same location, but the Earth has rotated away underneath them, so they're a little bit off, and so during one day they basically circle the Earth in two directions. So since we know that it's probably going to hit in the early noon or early morning or noon or slightly later noon around that time, we can tell that the places it only passes over in the later afternoon or evening are less likely, like South America or East Asia. Now, a few places were of course excluded from the beginning because this orbit has an inclination of only 42 degrees, so anything north of 42 degrees north and everything south of 42 degrees south is already impossible to hit, so unfortunately I will most definitely not be able to see it fall down. Which, while the probability that anything will actually hit anyone is incredibly low, the probability that you'll be able to see it fall down if you live south of 42 degree north and north of 42 degree south is actually possible. It will start burning up at a relatively high altitude, and so it will be visible from relatively far away. Also, at this point it will still be relatively big. It will then melt down to only leave a few tiny pieces, but when it starts burning up it will be relatively big and thus create a lot of light. If that also happens near the morning or evening time, then it will also be lit by the sun, and you'll at the same time have a relatively dark sky, so you will see a good contrast, but either way you'd have to be relatively lucky to see it. Again, we can't tell for sure when it's going to come down or where. We know that when it comes down it will be relatively sudden. Again, the atmosphere increases in density exponentially, so at some point it will just pass through some threshold altitude where the opposite side of its orbit will just suddenly decrease by some 30 kilometers or something, and then on the opposite side of the orbit it will just start slowing down to the point where it's no longer in orbit, it's just going to crash down. Of course, you could say that there's a slightly higher probability that this happens on the lower side of the orbit rather than the higher side of the orbit, since obviously that will pass through any threshold altitude sooner, but then these are constantly shifting and also getting closer and closer to each other as the orbit is more and more circularized by aerodynamic forces, which of course only works in an approximation as long as these forces are relatively small compared to gravity. If you get to the point where it actually starts crashing down, this approximation no longer really works. It will basically overshoot the circularization and just fall into the Earth. Now I've added a very rough simulation as to what such a super shallow re-entry might look like to this video, and if you look at it you can see it drops below some critical altitude and then it very suddenly goes steeply downwards, and that's also why it's so hard to predict and why this is just a very rough simulation of what it may potentially look like, because we just don't know exactly what that critical altitude is and we don't know at which angle it will actually hit that altitude. Either way, it will be very interesting and not very dangerous, so generally don't panic, maybe keep track on some news sites, and eventually there might be something interesting coming out of this, and I might make a wrap up about this afterwards if it ends up being incredibly interesting or unexpected. Either way, that's it for today, a little special to current events. Next video I will go back to theory around rocket design that isn't related to events happening that very day. If you have any questions about spaceflight or the related physics underlying it, I'm always open for any requests, and as always, thanks for watching.